Hello everyone, it is our pleasure to present our work, Prompting Large Language Models with Answer Heuristics for Knowledge-Based Visual Question Answering. The authors are affiliated with Hangzhou Dianzi University and Hefei University of Technology, China. Our poster is present at Wednesday p.m. 250. The paper and source code can be referred to the given URLs. In this paper, we present a general framework called PROVIT, which is short for Prompting Large Language Models with Answer Heuristics. We highlight our contributions as follows. First, PROVIT used GPT-3 as an implicit knowledge engine for knowledge-based VQA. Second, to better activate the few-shot learning capacity of GPT-3, we introduce answer heuristics to prompt GPT-3. Third, extensive experiments show that PROVIT outperforms all the existing state-of-art methods on two benchmarks. Last, PROVIT is highly reproducible. All we need is a single GPU and a number of GPT-3 invocations. Unlike traditional VQA tasks, that the visual questions are more correlated to the content within the image, the task of knowledge-based VQA is introduced to validate its model performance to leverage external knowledges. For example, a typical knowledge-based VQ example shown in the bottom right. To answer which US president is related to the object in the image, the model must not only recognize that there's a teddy bear in the image, but also know that the first name of the President Roosevelt is Teddy. A straightforward solution for knowledge-based VQA is to retrieve knowledge from explicit knowledge bases, such as structured KB like ConceptNet and unstructured KB like Wikipedia. Given a question and an image, retrieval-based methods first fetch related knowledge from the KBs. Then, a VQA model performs joint reasoning over the retrieved knowledge, the image, and the question to predict the answer. However, the performance of this method is limited for the two reasons. First, the required knowledge may not be successfully retrieved from the KBs. And second, even if the required knowledge is retrieved, plenty of irrelevant knowledge is introduced, which hampers the learning of the VQA models. Recently, some works like Pika utilizes large language models, for example GPT-3, as an implicit knowledge engine to address the task. In this direction, Pika is a pioneer work. It prompts GPT-3 with image captions and follows the paradigms of the few-shot in-context learning to resolve the task. Without model training, Pika makes GPT-3 to adapt to the new task. And compared to the retrieval-based methods, Pika delivers significant performance improvements. Despite the promising results achieved by Pika and its successors, we argue that they have not fully activated GPT's ability for the following reasons. First, the generated captions often fail to cover the necessary information in the image. Consider the example in the figure. The caption, "A group of people walk in the city square," contribute nothing to answer the question, "What fruit come from these trees?" In this situation, GPT-3 has to make an aimless and biased guess to answer the question. Second, the in-context examples used in the prompt are non-optimal, which restrict GPT-3 to understand the task clearly. So, it is natural to ask, is it possible to endow GPT-3 with some heuristics to enhance the capacity of GPT-3 for knowledge-based VQA? In this paper, we propose the PROVIT framework with introducing two types of answer heuristics. Giving a vanilla VQA model trained on a specific knowledge-based VQA dataset, answer candidates is top K answer and its confidence score pairs that a VQA model predicts. And answer-aware examples refer to top n nearest training samples to the testing samples based on the similarity of the latent feature of the VQA model. The generated answer heuristics are integrated with the questions and captions to format a structured prompt to instruct GPT-3 to predict an answer for the testing sample. Here are our experimental results on OKVQA dataset. To implement Profit, we use an improved Macan model with careful parameter tuning as our VQA model used in the first stage. Note that the model is trained on one consumer-level GPU. The model reports a 53-point accuracy, which is on par with current state-of-art methods. In the second stage, we inherit most configurations from Pika as our default settings. We conduct extensive ablation experiment for Profit on OKVQA, and from the result below, we can conclude that our answer heuristics are sufficient and efficient resource for prompting GPT-3 to address knowledge-based VQA. Here are the main results on two datasets. On OKVQA, Profit outperforms all the compared methods by a distinct margin, and is 13 points higher than Pika when both methods use GPT-3 as the only knowledge resource. Compared to Kate and Revive, which utilize GPT-3 and other external KBs together in a complex compartmentalize, Profit is much simpler and more effective. Compared to Flamingo model with 80 billion parameters, Profit delivers a 3-point improvement and is more resource efficient from the perspective of reproducibility. Flamingo is trained on over 1,500 TPU chips for 15 days, which is unaffordable for most researchers. However, Profit uses only one GPU to train a VQA model for 4 days, and only require a certain number of GPT-3 invocations. On a OKVQA dataset, Profit also surpasses all the existing methods on both the direct answer and the multiple choice metrics. And the variant Profit MC, especially designed for the multiple choice, achieve a significant performance improvement over the other methods. That's all for the introduction of our paper. Thanks for listening.